All right. Statistics Lesson 5, the normal distribution. So it's important to know that many things in life, including volume, mass, time, all have common characteristics in how their data is distributed, and even length, or just many things in life. And so what they noticed is that they all had this similar pattern. And so here is 3 different graphs: weights of infants, time taken to complete assignment, height of students. And you'll notice they all have this general shape to them, right? Where you have a lot near the average, and then we have our extreme values in the end. And it makes what we call a bell curve. In each case, the frequency polygon of the data results in a bell shape, what we call a bell shape. So the normal distribution is this bell-shaped curve. So data which can result in frequency polygon with a bell-shaped curve is said to be normally distributed. Normally distributed. So it's a normal distribution, something that's very common. And so the normal distribution is referring to the normal curve or the bell curve. And it's used very often in statistics and marketing and research to make predictions of what could happen, right? So if you were on this end, what's the probability of that happening? So it's very common to use this statistics in real life. Okay, so understanding the normal distribution curve. Here's an example where we have 100-watt light bulbs from Glow Bright, and these light bulbs, they have different lifetimes. And so after testing 44 bulbs, he calculated the mean life to the bulbs to be approximately 900. So this is the average, 900 hours is the mean, or your average lifespan. And the standard deviation, remember, is a spread from the mean. It's 50 hours. Okay, so here's the 44 light bulbs. So the histogram was created. It says verify, but what basically they took data how many are between 750 and 800, and there was one piece of data between how many were between 800 and 850, and so forth. And this histogram was created. So we're going to use the histogram here to fill in this chart. So how many were less than 800, and that was 1. How many between 800 and 850? That is 6. How many between 850 and 900? Looking at the graph. Oh, keep going. There was 15. And 15 between 900 and 950. Between 950 and 1,000. Again, there was 6 pieces of data, and 1 greater than 1,000. So percent of bulbs in the interval. So there's a total of 44 light bulbs. So this would have been 1 over 44. We're just going to figure out, okay, what percentage is that with our calculators. 1 over 44. Oops, let's get out of there. 1 over 44 times 100 gives you 2.27%. 2.27%. The next one, we have 6 out of 44. 6 divided by 44 times 100 is 13.6%, or 64. 13.64%. Then we have 15 out of 44 in this category. That's already calculated there for us. It's 34.09%. Again, this category again is 6 out of 44, and we have 1 over 44, and we already calculated what percents those were. So we have 13.64% and 2.27%. Okay, now these are very common. These are very similar to the actual percentages in a bell curve. So we're going to continue on. So using mean equals 900 and mu equals 50, write the following numbers in terms of your mean and standard deviation. So 950 is the same thing as taking our mean and adding 1 standard deviation. So our mean plus 1 standard deviation. 850 is our mean minus 1 standard deviation. 800 would be our mean minus 2 standard deviations. So we want to subtract 2 times 50 or 100. 1,050, we take our mean, which is 900, and we want to add 150 to it, so that would be 3 standard deviations. So complete the normal distribution based on that. So we have 900, 950, 1,000, 1,050, going backwards, 850, 800, and 750. Okay, so 34.09% in those two categories, and we had 13.64% on these ends, and we had 2.27%. 2.27%. Okay, so we're going to write in our number of standard deviations from the mean. So the mean, 0 standard deviations from the mean. 950 is 1 standard deviation away, 1,000 is 2, and 1,050 is 3. Now, 850 is 1 standard deviation. Because we're going to the left, we're going to actually make it -1. 800 would be -2 standard deviations from the mean, and -3. These numbers here are going to be really important in the future, and what we're going to call them are Zed scores. Zed scores. And the Zed scores tell us how many standard deviations from the mean we are. Okay, in terms of our mean and standard deviation, so your mean is the middle. 1 standard deviation would be mean plus 1 standard deviation. 2 standard deviations over, or to the right, is your mean plus 2 standard deviations, and then our mean plus 3 standard deviations. Going the opposite way, 1 standard deviation to the left is our mean minus 1 standard deviation, and mean minus 2 standard deviations, and mean minus 3 standard deviations. And that's how we get our values, right? If we know our mean is, say, 900, and I want this value here, and our mean was 900, standard deviation 50, then this would be 950, a mean plus 1 standard deviation. So the curve above is based on one particular example and is a good approximation for the standard normal curve. On the next page. So here's some important notes. I'll help you sift through this, and we'll talk about what's important here. For population data, which means mean and standard deviation sigma, the normal curve is denoted by n. And what you need to know is a symbol for mean and a symbol for standard deviation. Don't have to worry about that symbol n, but there is a difference between, there is a different probability distribution for each value of mean and standard deviation. And we're going to talk about that. Okay, moving on. You do not need to know, this is an equation that would actually graph the curve on your calculator, which you do not need to know. What you do need to know is, let me grab my highlighter, that the distribution represented by the standard normal curve has a mean value of 0 and a standard deviation of 1. Okay, so when we draw that, we set our 0 as our middle, our standard deviation as 1. Okay, so here, these Z scores are, when we ever are working with our Z scores, the mean will always be 0 and the standard deviation is 1 because we want the 0 to be the middle. So here, looking at this data, let's fill in the chart. The mean value of the data is 0 and the standard deviation is 1, positive 1. What percent of the data is above the mean? So if we, above the mean is all of this. So if we added all of these together, what percent is above the mean? So if you want, let's grab our calculators and let's check. So we have 34.13% plus 13.59% plus 2.15% and another 0.13%. And that equals 50%. So that means 50% of the data is above the mean. 50% of the data is above the mean. Meaning, what percent is below the mean? Also 50%. What percent of the data is within one standard deviation of the mean? Within means one both directions. So what percent is all within one standard deviation? Well, it'll be 34.13 plus 34.13. That's 68.26. 68.26% of the data is within one standard deviation. Next question is what percent of the data is it within two standard deviations of the mean? So now we're looking at from -2 to +2. What percent of the data is within two standard deviations? So grabbing your calculator, we can add those percents together. 13.59, and there's two of those, plus 34.13, and there's two of those. So 95.44% of all your data will be within two standard deviation. So almost all your data. Okay. Now within three standard deviations, well, let's add those together. So we have, now this time, we're looking at between -3 and +3. What percent of our data is within three standard deviations? So that's what we want to do. So we want to add in those values together. So grab your calculator. So we have 13.59, plus the 2.5%. Let's start that again. So there's 2.15% times 2 plus 13.59% times 2 plus 34.13 times 2, because there's two of them. So 99.74% of the data is within three standard deviations of the mean. Okay, what percent of the data is between 1 and 2 standard deviations above the mean? So just between 1 and 2 would be 13.59%. And last, what percent of the data is between 1 and 2 standard deviations below the mean? That would be the same, 13.59%. Okay, let's talk about these properties. These properties are so important. They maybe should go on a study sheet. They should be memorized and just known. Okay, so let's look at, there's three different ones. Five different things we need to know. One, the total area under the curve is equal to 1. Right? And if we change that to a decimal, that would be 100%. So if we add all the decimals together, so I'm looking at this here, before they were percents, all of these added together equal 1. Change that to a percent, that'd be 100%. So the total area under the curve is equal to 1. Next, the normal curve extends infinitely to the left and to the right. So it doesn't actually touch this horizontal axis. It keeps going. It gets closer and closer and closer and closer, but it never actually touches. Okay? So that's important to know about the bell curve. So the curve infinitely extends infinitely. The normal curve is symmetrical about the mean. That's really important. So that means 50% is to the left and 50% is to the right. All the data is represented by the area under the curve. So area is another way we can talk about underneath the curve instead of just percentages or probabilities. And in a normal distribution, this is important, the mean, median, and mode are the same value. They are the same value. Okay, so let's look at this example. A nurse records the number of hours an infant sleeps during a day. He then records the data on a normal distribution curve shown below. The values shown on the horizontal axis differ by 1 standard deviation. So what would be the mean? Well, remember, mean is in the middle. Mean is in the middle, so our mean would be 12. Okay, and what is our standard deviation? Well, our standard deviation is always our distance between each Z score, right? This is Z score 0 here, -1, -2, -3, 1, 2, 3. So what's that difference in between our values for each one? And it's 2, right? So our standard deviation would be 2. So what are the values of A, B, C, and D? Well, so if we're going backwards, we're subtracting 2. So this would be, B would be 8, and A is 6. B is 8. Adding to the other direction would be 16, and adding to again is 18. C is 16, D is 18. So what percent of the days to the nearest hundredth does the infant sleep between 12 and 14 hours? Well, remember from our curve before, we're going to use that same curve because that's true for all normal distributions. So we're talking about these percentages here are the same for all normal distributions. So let's look here. It says between 12 and 14 hours. Between 12 and 14, that's between 0 and 1. So looking at our curve on the other page, between 0 and 1 was 34.13%. So you might want to just fill in these percentages. We have 34.13% and 34.13%. Okay. Between 1 and 2 standard deviations was 13.64 or 13.59%. So let's fill these in because we're going to have to answer some questions on that. And then we had 2.15%, 2.15%, and 0.13%. Okay, so what percentage days to the nearest hundredth does the infant sleep between 12 and 14? So between 12 and 14 would be 34.13%. Between 8 and 16, that's within 2 standard deviations of the mean, right? So that's 13.59 plus 34.15 plus 34.15 plus 13, or sorry, that's 1 3 over this. These are 3's. And plus 13.59. And so we already looked at that before on the previous page, and that was 68.26%. Oh, nope. 2 standard deviations was 95.44%. We added those together. And then less than 6 hours, that would be here, 0.13%. So why is it not possible this time to determine the percentage of days that the infant sleeps for less than 13 hours? Well, if you look here at 13, 13 wouldn't, because this is a normal, this is curved here, 13 hours, you can't just divide 34.13 in half, right? It's going to be, you can't, because that wouldn't represent that area, the one to the left here is more to the than the one to the right. And so right now we only know the percentages for exactly 1 or 2 or 3 standard deviations away from the mean. So let's write that in words. We do not know the area under the curve for increments of less than 1 standard deviation. We don't know the area under the curve for less than 1 standard deviation. We only know the 1 standard deviations. So in order to answer that part E, we need this concept of Zed scores. Moving on. So what are Zed scores? Well, Zed scores for a particular data value is a number of standard deviation the data value is above or below the mean. Okay, and we talked about that a little bit before. So the Z score for a particular data value is the number of standard deviations above or below the mean. If it's positive, a positive Z score means above the mean, and a negative Z score means below. So calculating and displaying Z scores on the normal curve. So the data value of 18, is how many standard deviations above or below the mean. So let's look over here. So 18 was, this is 0, is our mean. 1, 2. So 18 was 3 standard deviations above the mean, meaning it would have a z-score of 3. At the value of 8 in the previous example, it's 0, -1, -2. So it's 2 standard deviations below the mean, meaning it would have, so if it's 2 standard deviations below, so its z-score would be -2. 12, 12 was 0. So it's 0 standard, the z-score would be 0. If it's 0 standard deviations away from the mean, it is the mean, its z-score is 0. And 13 then, well, 13 now would actually be 0.5 standard deviations. It's halfway. So 0.5, and that was above the mean, so it'd have a z-score of positive 0.5. So here's that from the other page. So this is where 13 was. So let's fill in our z-scores. Our z-scores go down here, 0, 1, 2, 3, and we had -1, -2, -3. So mean is in the center. 14 would be mean plus 1 standard deviation, mean plus 2 standard deviations, and mean plus 3 standard deviations. The other direction, 10 would be a mean minus 1 standard deviation, mean minus 2 standard deviations, and mean minus 3 standard deviations. Okay, so our 13 would have a z-score of 0.5. So how can the z-score for a data value of 13 be determined? Calculate the z-score for the data value of 13 and list both the data value and the z-score for the normal curve above. So we did that. So what I could write is z-score, and I can write the actual value. So 13 equals 1 half, or 0.5. Now there is a formula to calculate this, our z-score. So if you know your mean and standard deviation and the value you want to determine the z-score for, we have this formula. Now this formula is on your formula sheet. It's really important. You will be using it a lot in this unit. So highlight that. But it is on your formula sheet. It is on your formula sheet. So let's talk about what each thing means. Z is that z-score. Remember, z-score tells you your distance from your mean. X is the particular data value, mean, and then we have standard deviation. So the z-score indicates the number of standard deviation the data value lies from the mean. A positive z-score means above. Negative z-score means below the mean. Okay, so this is that same chart again. So the 68, 95, 99 rule. So you don't have to know the percentages exactly, but you need to know that approximately 68% of the data is within 1 standard deviation, 95% of the data is within 2 standard deviations, and 99% of the data is within 3 standard deviations of the mean, approximately. 1, 2, 3. Okay. So here, it says complete the following. Approximately 68% of the data lies between a z-score then of within 1 standard deviation, so that'd be -1 and 1. So between -1 and 1 is that 68%. The 95% is within 2 standard deviations, so that would be between a z-score of -2 and +2. And the 99% is within 3 standard deviations, so -3 to 3. Okay. So let's look at some examples now using this formula to calculate z-scores. So the heights of in centimeters of 5 starting members of the Wolfhounds basketball team are the following. If the mean height, so let's write that to the side. Whenever I'm given a mean and standard deviation, I always write that down first. So mean is 190 and standard deviation is 15. It says calculate the z-score to the nearest hundredth for the tallest player. Then the calculation of the z-score for the shortest player is shown. So let's now do the z-score for the tallest players. The tallest was 212. So our formula for Z-score is x minus my mean over my standard deviation. So we want the Z-score for 212. So x is my particular score. So in this case, x is 212 because I want to calculate the Z-score for 212. The mean was the 190, and standard deviation they gave us was 15. So let's plug it in. 212 minus 190 all over our standard deviation of 15. Now, if you plug this into your calculator, you have to remember invisi brackets on the numerator if you want to do it all at once. Otherwise, just do it in parts. 212 minus 190, enter, divide by 15. Or we could go bracket 212 minus 190, bracket divided by 15. And so let's round to the nearest, let's always go to two decimal places. So 1.47. 1.47. So what that means is we are 1.4 standard deviations, 47 standard deviations above the mean. That's what that means. Okay, let's try some more. Tony's midterm marks are shown below. Together with the class mean and standard deviation for each subject. By calculating the Z-scores, you can determine which class he's actually doing better than compared to his classmates. So here's his mark for each one, the mean for each one, and the standard deviation for each one. So first, let's find the Z-score for math. So remember our formula is x minus our mean, score minus our mean over standard deviation. So for math, our score is 74 minus my mean of 68 all over 12. So in our calculators, 74 minus 68 divided by 12 is 0.5. So he's 0.5 standard deviations above the mean. In chemistry, so his score minus the mean divided by the standard deviation. So remember in your calculator, if you're going to type this in all at once, you need brackets around the numerator. Divided by 14 gives you 0.43. 0.43 standard deviations above the mean. So in both of these, he is above class average. And physics, his mark is 68 minus the mean in the class is 66 over the standard deviation of 11. So if I can do it in two parts as well, so 0.18. So in all of these, he's above class average, but he's doing the best in mathematics. So Tony performed best in math as his Z-score is highest in that class. So Tony performed best in math since his Z-score is highest in that class. The average mark on an English exam was 63, so that's the average. So average means mean. Standard deviation was 12. If the marks were normally distributed and Z-score was awarded of 1.5, then what was the student's actual mark? Okay, so here's our formula. Let's plug in what we know. We know his Z-score is 1.5. We're looking for x, so minus x minus 63 over 12. So if we want to get x by itself, the first thing was we need to get rid of this fraction. So we need to multiply both sides by 12 first. So 1.5 times 12 is 18. 12 times 1.5 is 18. So 18. So now these are gone. So that equals x minus 63. And then our last step is to add 63 to both sides. plus 63 to 18 gives me his mark was 81 in that class. So therefore, the mark was 81%. That was his actual score. Almost done. 2 more questions. The weights of a large shipment of cantaloupes are normally distributed with a mean of, first thing I'm going to write down, 2.3 kilograms. And the weight of a particular cantaloupe is 1.7 kilograms. So they give us the actual weight. That's our X score, which is 1.01 standard deviations below the mean. So that means our Z score is negative 1.01. Determine the standard deviation. Okay, determine the standard deviation. So let's write out our formula and sub in what we know. So Z is equal to X minus our mean over our standard deviation. So Z is negative 1.01. Our X score is 1.7 minus my mean is 2.3 divided by our standard deviation. Okay. Now what can we simplify? Well, for starters, I can actually subtract what's on the numerator. So 1.7 minus 2.3 is negative 0.6. So I have negative 1.01 is equal to negative 0.6 divided by our standard deviation. We want to get standard deviation by itself, but we can't solve for it if it's on the denominator. So we have to get rid of that fraction. So our first step here is multiply both sides by the standard deviation. So you have negative 1.01 standard deviations is equal to negative 0.6. Okay, so now we want sigma by itself. It's being multiplied by negative 0.11. So we're going to divide both sides by that to get sigma by itself. So negative 0.6 divided by negative 1.01 gives you positive 0.59 kilograms. And so that would be the standard. So therefore, the standard deviation is 0.59 kilograms. Okay, the marks on a math exam at a university were found to have a mean of 52 with a standard deviation of 12. A professor who thought the exam was too difficult decided to adjust the original marks by raising the mean. So the new mean is going to be 65, but reducing the standard deviation to 10. And leaving the Z scores unchanged. So the Z scores are going to be the same. So same Z. What would be the new mark for a student who received original mark of 34? So his original score was 34. So our goal is, in order to find this guy here, we know the Z scores are the same. So I'm going to find the Z score of the first, of the actual. That would be the same Z score we can find as mark. So our Z score would be our mark minus the mean all over the standard deviation. So with my calculator. So 34 minus 52, bracket divided by 12. Is negative 1.5 standard deviations below the mean. So we know now these guys are the same, so his Z score is also negative 1.5. So we can now solve for the new mark. We know standard deviation is negative 1.5. We're looking for X minus the new mean is 65 divided by the new standard deviation of 10. So to start off, we have to get rid of this fraction to get X by itself. Multiply both sides by 10. It's going to give me negative 15 is equal to X minus 65, and then add 65 to both sides, which gives us 50. So the new mark would be 50. He's still at the same spot relative to his whole class because he's still negative 1.5 standard deviations below the mean, but now his mark is 50. So therefore, the new mark is 50. And that's it for this lesson.